All right, so let's go to the next slide. First of all, thank you for joining us here today. There's over 200 people here to learn about the moon. What Artemis and the next era of lunar exploration will provide for us is an opportunity to explore a brand new terrain on the moon, the lunar South Pole. Between a series of robotic missions, of course, crewed missions to the South Pole, we had an inflection point in our understanding of the moon, its history, its environment, and how we use that history and environment to advance our understanding of our place in the solar system is a unique opportunity that's presented at the South Pole of the moon. So what I'd like to do over the next 14 minutes and 18 seconds is walk through a little bit about the moon. What do we know? What don't we know? And how we can get to a place where the science that the 220 people who are on this call want to do is achievable. I'm thrilled to, in looking through the attendee list, to recognize a handful of names, but many, many new names. One of the joys of lunar science is that it is a big tent. We have an opportunity to do a lot of different types of science, not just the traditional hard rock geology, but indeed the kinds of science that utilize the environment to understand how humans respond to the environment, the dynamics of the moon and this incredible corner of our solar system. And so I want to leave everyone at the start with the promise that the lunar surface and the lunar environment is one of the most compelling targets in our solar system. And so the opportunity we're presented with over the next decades, and hopefully decades upon decades, is really limitless. And it's only limited by our source of inspiration and our creativity to use this environment to benefit all mankind. Let's go to our next slide, please. As a start, I just want to kind of remind everybody that while we know very little about the moon, there are a lot of science questions that we have to go to the moon to understand. We also do know a lot about it. We know more about the moon than I think we give ourselves credit for, and I'll talk a little bit about what we do know about the moon, and largely through the lens of the Lunar Reconnaissance Orbiter, a spacecraft that we've now had at the moon over for 15 years. We've done a lot to understand the lunar surface and its environment. So first and foremost, I want to remind everybody, particularly those that might be new to, broadly speaking, lunar science, that we do know a lot about the moon and its surface, and that the moon is not Mars, and that what we've learned about Mars is incredible over the last several decades, but that the moon is very different from Mars. It behaves differently, with the lack of an atmosphere, the lack of flowing water over its history. The moon's surface is shaped largely by the interactions with the space environment, but that the moon is not homogeneous. It does vary from space, from location to location, but again, with the data we have, we understand it. I would like to remind everybody that over the last many decades, there are several excellent syntheses about what we know from the moon. New Views of the Moon 2, which came out last year, is an excellent update to New Views of the Moon 1 from 2006, shaping our understanding of the moon in this new environment. All of that comes on the heels of the excellent Lunar Sourcebook, which is available at the link provided there. And so for those that are new to lunar science, I think these are excellent places to start in your journey to understanding the moon. Let's go to our next slide, please. I like to pause always and reflect on what we learned from Apollo. And while the information that we get from the samples is key, Apollo was a big scientific tent. Several missions, not just to the moon, of course, in Earth orbit, lunar flybys, lunar orbital missions, of course, our surface missions, conducted a treasure trove of scientific experiments, not just collecting samples, but of course, deploying experiments, conducting experiments in lunar orbit and in transit to and from the moon, really paved the way for what we think we can do and build on in the Artemis era. The pictures at right, of course, are from the Apollo Light Flash Moving Emulsion Detector, a mouthful, showing that just the act of having humans in space provides a platform for science. Of course, we've done that now over several decades with the shuttle and the International Space Station, and we can, of course, continue that going deeper into space at the moon with Artemis, and of course from the Lunar Gateway. Let's go to our next slide, please. So we build on Apollo. We look towards what we can do. We've, of course, had the Apollo missions to the surface. We've had several landed missions, sample return missions internationally. Of course, orbital missions. I'll talk about LRO in a moment. And the types of science that we can do from the moon really expands across the full spectrum of things that NASA's interested in. Of course, we have biology, material properties, getting down to the nitty-gritty of the structure of the lunar surface, the history of the lunar surface, going back to the formation of the moon, Now we are in a position where we have a robust set of orbital observations as well as, of course, the samples. We also can see, thank you, Ricky, that with additional time from LRO, now orbiting the moon, we are looking at what can be gleaned from long duration orbital observations. And I'll remind everybody that the data set that we have from LRO grows and is made available at a monthly cadence from our camera and every 3 months from all of the instruments available at a link that I'll show in the next slide here. Now, when we release the data, it's put out to the world. Ricky, next slide, please. And for use. And so for those that are interested in using LRO data, I'd encourage folks to reach out to myself, to Dr. Maria Banks, to learn more about how we can learn data. And again, we have everything from high resolution images to radar data, as example, shown at the right-hand side there, to radiation data from our crater instrument. And all that data, again, is made publicly available fairly rapidly. Next slide, please. So what have we learned over 15 years? Well, quite a lot. I'd like to think that we have rewritten our understanding of the lunar surface and environment over the last 15 years, from the detection of thermophysical anomalies due to the formation of recent craters, as folks may have read about recently, the detection of pits, caves, these unusual volcanic features called irregular mare patches, which may represent young volcanism or certainly a distinct form of volcanism that LRO has revealed in its entirety. Again, compelling targets for future exploration. We've made measurements of the solid body tide of the moon. We've measured the surface of the moon in different wavelengths that we had never measured globally before. And of course, looked at the unusual compositions that compel us to understand more about the moon and its history. I'd say for this environment, for this team, of course, the radiation environment and its place, the moon's place in our corner of the solar system are some of the most interesting, and I think will provide the basis for several investigations when we get to the lunar surface for how the moon responds to being in the deep space environment. Next slide, please. So I just want to highlight some of the data sets that we do have. One of the benefits of having a long-lived orbital spacecraft is to detect changes. We've imaged new impacts that have occurred over the life of the LRO, so now we have an understanding of how the moon ages over human timescales, not just over billions of years, but over tens of years. I think the LRO data set has also forced us to re-examine what we assume to be true about the moon and maybe call into question some of those long-held beliefs. And so I'd also encourage this audience to come at the moon with new eyes and not just assume that, well, because a paper written in 1973 said X, it must be true. We should challenge all of our long-held beliefs about the moon and endeavor to conduct new science investigations to challenge those things. Of course, the volatile story at the moon is compelling. One of the reasons why we're going to the lunar surface, and particularly the lunar South Pole, which calls into question, the very nature of water across the solar system and how it got not just to the Earth, but of course to the moon and its poles and its interior. Next slide, please. So quickly looking at some of the different data sets, everyone's probably familiar with these beautiful high-resolution images from the Lunar Reconnaissance Orbiter camera, narrow-angle camera. This is an image of the Apollo 12 landing site and just an example of what we can glean from the surface. Not only do we see the hardware left behind, the descent stage of the Apollo 12 lunar module, but of course the Surveyor spacecraft, the ALSEP experiments left behind, the boot prints of the astronauts, and of course the natural environment, the rocks and boulders that crew members explored on Apollo 12. And of course, when we look at future sites at the South Pole, future exploration targets for our crew and robotic explorers. We have images across the entire moon of varying resolutions and of course varying sun angles, allowing us to discern the surface in ways that we could only dream of prior to LRO. Next slide, please. It's one thing to measure the images of the surface, but of course we want to put that into context of the shape. We have topography at ranges of scales thanks to the LOLA instrument and stereo images from LROC. This has enabled us to understand how the moon, basically the shape of the moon, and prepare for future robotic explorations, whether it's static landers, rovers, crews. All of this topography helps us better prepare for the inevitable future exploration of the moon. Next slide, please. Just some examples of what we can do with this topography data, of course, is it's not just shape, but then derived products, slopes, roughness, all at a precision that allows us to not only measure the flexure of the lunar surface due to tides, but also, again, see the descent stage of the lunar modules on the surface thanks to the stereo images from LROC highlighted in the next slide, please. All of the topography allows us to paint the moon with the data we've collected, understand areas that are in shadow, and of course, plan for and execute future robotic missions. The fly-through we're seeing at the bottom right is, of course, of the Apollo 17 landing site, kind of highlighting the scale with which we can use the topography to plan for these upcoming missions and revisit places we've been. Next slide, please. It's one thing to have image data and topographic data. We also, of course, have an incredible thermal data set, thanks to the Diviner instrument, which has been measuring the temperature of the lunar surface now for 15 years. There's several derived products, but potentially of most interest is to understand the environment, the special environment of at the south pole of the moon that has both extreme lows in temperature, some of the coldest temperatures recorded in the solar system, as well as more moderate temperatures. And so understanding the environment that we're sending our future explorers is not only critical, but also becomes a science investigation in and of itself. We have maps of seasonal of temperature changes over summer and winter, really highlighting the dynamics of the polar environment that we're going to be exploring. Next slide, please. This is an animated GIF or GIF of just the normal day-night cycle across the whole moon. And of course, you see from here that there are some areas that don't cool off quite as much as the night passes across. These, of course, we now know to be rocky areas. And so the temperature measurements that we get from Diviner not only shape our understanding of the thermal environment of the moon, but also the thermophysical environment of the lunar surface. Again, something that future explorers will be immersed in, but we can prepare for thanks to the data set that we have here. Let's go to the next slide, please. Okay, so we're turning our sights to the South Pole, this really unique environment. Not only do we have extremes in temperature, as was showed before, but of course extremes in lighting. I want everyone to notice, it stands out quite vividly, how striking the craters are that are at the South Pole. One thing I want everyone to walk away from is not, oh my goodness gracious, look at all of these craters. The density of craters at the South Pole is no different than any other ancient terrain on the lunar surface. It's just that the lighting conditions exacerbate it, highlight the ruggedness of the South Pole. But in fact, it's no different than really any of the other ancient terrains on the lunar surface, similar to where we explored with Apollo 16, for example. And so with this data we have, and indeed the highest density of data observations we have for the moon are at the lunar poles, we are in an excellent position to explore these environments. Next slide, please. I'd also point out that we have these visualizations. We have the data, we can use it to tell stories, to understand the environment. This is an example landing site at the south pole of the moon over several days, showing how the lighting conditions change. Recall that at the South Pole, the sun will never rise more than a few degrees above the horizon, casting long shadows. But of course, we use these long shadows as guideposts to not only identify features, but where boulders and surface features stand out. So our eye is drawn to the craters, but our eye also can be drawn to the hazards and of course the inviting environment that we'll be exploring with upcoming robotic and crewed exploration. Next slide, please. Of course, the beautiful vista. Imagine yourself standing now at the South Pole of the moon looking back to the Earth. This is a recreation of what that view would be like. You can see not only the low sun angle, but the grazing angles and indeed the disappearance of the Earth from view. Is a different environment than Apollo. Lighting conditions will be distinct. The Earth visibility will be distinct. I'd say that it's not a challenging environment, but one that we have to constrain and understand using the data that we have. I like to think of the South Pole of the moon as being a little bit like freeform jazz. We can understand it, you can notate it, but it doesn't always follow the same patterns as traditional music or as traditional landing sites at the equator of the moon. So as much as there may be challenges, these are challenges that we can face with the data that we have in hand. Next slide, please. So we have a lot to learn from the moon, and I hope over the next few hours, we all have an opportunity to explore, ask questions, and learn more about this incredible environment. The next several decades are going to be thrilling. I cannot wait to see what happens. But this will be only as complicated as we want to make it out to be. The moon and its data are ours. We have it. It's up to us to interpret it properly, to use it properly, and not, I think, assign things to the moon that are unrealistic. Over the last several decades, NASA has invested in archiving the data, getting this incredible data set, making it available, understanding the samples that we have, and building a workforce to enable Artemis and CLPS in the future era of lunar exploration. I would just say that we have a number of subject matter experts across NASA who are here to help broaden this community. As the great American poet Vanilla Ice once said, if you've got a problem, we can solve it. And so I would encourage everyone here to reach out to myself, my colleagues, and let's go explore the moon. And with that, I will turn the ball back to you, Kevin. Thank you.